Hello friends, in this session we will discuss about the statistical quality control. And under this statistical quality control, we will discuss about the control charts for variable and control charts for attributes. And later on in the next session, we will discuss about the single sampling curve and double sampling plan, that is OC curve, operating characteristics curve. Now, the control chart for variables. There are two types of the quality parameter. One is known as variable and other one is known as attributes. So variable are those quality parameters which can be directly measured in terms of number or in terms of the continuous number. This may be the length, width, thickness, internal diameter, external diameter, etc. But the quality parameter which cannot be directly measured can be shown in terms of the attributes, and in that case we can only judge that quality is good or bad, this is pass or fail, this is defective or the good product. So in this way we can divide this quality parameters into the two category. One is variable, other one is attributes. Now I have already discussed in the first session of the quality management, that is in the previous session, that this control chart concept was given by the W.H. Watt in 1920 in a Bell Telephone Laboratory. And they have discussed about the control charts in terms of the upper control limit, lower control limit, etc. And in this case we consider the plus minus 3 sigma limits of the upper control limit and lower control limit and the total deviation. Now see what are the different sources of variations in the product, why the different quality parameters varies in the product. There may be the different sources of variation. One is variation due to the process included, the tool wear, way of operation, tool vibration, jigs and fixture. This is due to process, this is due to process. So this is one of the sources of variations. And then second source of variation is material, due to irregularity in material. This may be due to change in the property like tensile strength, ductility, malleability, hardness, toughness, thickness, porosity and moisture content. So these are due to the materials property. Then maybe the variation. Then the environment is the third source of variations, and this may lead to different temperature, light, radiation, humidity, etc. Then variation due to operator. This may be due to variation in skills, motivation and wages of the different workers. Then the inspection, way of the inspection and the calibration of the inspection equipments and the quality standards, inspection device, etc. So these are the five sources of the variations, and these sources leads to variation in the quality parameters of the product. Now what are the different types of variations? There are three categories of different types of variation. First one is known as within piece variation, second one is piece to piece variation, third one is time to time variation. Within piece variation means the one part of the product will be different from the other part of the same product. That means there is variation in the quality parameters. For example, if we consider the surface roughness, then surface roughness or the surface finishing may vary from one part point to the other another point in the same product. Similarly, if we consider about the depth of hardness, if you do the heat treatment of the particular material, then this depth of hardness may vary from one point to the another point in the same product. So this type of the variation is known as within piece variation. Now second type of the variation is known as piece to piece variation, and this may leads due to the tool wear or blunting of the tool. Initially if you use the sharp tool, then the surface finish will be very good, and later on due to the decreasing in the tool sharpness, there may be some problem in the surface roughness. So if we see that first 10 product or first 100 product or first 50 product, the quality will be different from the later on product produced on the same machine using the same tool. Now the time to time variations, the variations in the quality parameter which vary from one time to the another time. That means different times of the day or different day using on the same machine and using by the same persons or the workers on the same machine. So this may be due to laziness of the worker. After lunch, there may be less motivation to do the work, and before lunch, that means in the morning time there is a fresh environment and the quality may be the better. Similarly, there may be the effect of the humidity and temperature also in the later on in the second half the day of the day. The quality may be poor due to humidity and increasing the temperature, but in the morning time this may be the good. So this type of the variation is known as time to time variation. But during the time to time variation there may be the number of other factors also which may be considered for the variations. Now, chart techniques, how to produce the chart. In the case of the control chart for variables, we normally use X bar and R chart. And if the sample size is large, so for example more than 10, then in that situation we use X bar S chart. R is here used for the range and S is used for the standard deviation, and X bar is the mean value. X bar is the mean value. So if the sample size is small, then we use the X bar R chart. If the sample size is large, then we can use X bar S chart. Now, how to produce this chart? What is the chart technique? Initially, select the quality characteristics of the product, because for all the different quality characteristics, we have to draw the separate X bar R chart for all the different characteristics. But here we will have to select that for which characteristics we want to produce the X bar R chart. So this first step is the selection of the quality characteristics. Then choose the rational subgroup. That means what should be the subgroup size. That means suppose if we have selected the 100 product, then if we want to make a 4 subgroup size or 5 subgroup size, if we make 5 subgroup size, then what will be the number of subgroups? There will be the 20 subgroups. 20 into 5. If we use the 4 subgroup size, then we will have to produce the 25 subgroups. So the number of subgroups will be 25 and subgroup size will be 4. So in this way, what is the mechanism to select the subgroup size? That means for how many items in one subgroup should be there. So this is based on the again some statistical concept, and this is known as the central limit theorem. Later on we will discuss about the central limit theorem. But here at first we can see that if the subgroup size increases, then control limits will be closer to the center line. Closer to the center line. Why it will be closer to the center line? Again we will discuss when we will discuss the chart. Closer to the center line, and it will be more sensitive. If the subgroup size is small, then this will be wider and it will be less sensitive. Then what should be the optimal size of the subgroup? Now it also depends on the type of the test or the inspection. If suppose destructive type of testing is to be used, then in that situation we try to minimize the subgroup size. We keep 2 or 3 in one subgroup only, so that we can minimize the number of destruction. But as per the central limit theorem, if we take the sample from the non-normally distributed population or non-normally distributed lot, then this will be also non-normally distributed sample if this is less than 4. If we select the subgroup size 4 or more than 4, then definitely if we select the sample from the non-normally distributed population, but this sample distribution of the sample average will tend towards the normality and tend towards the normal distribution. So this is the reason that normally we try to take the 4 or more than 4 sample size. But if the sample size is very large, for example 10 or 12 in one subgroup, then in that case we do not use R. In place of R we use S. S gives the more reliable result. R depends on only two value in the subgroup. That is, one is the maximum value, another one is the minimum value, and other dimensions are not considered in R chart at all. This is the reason that R chart is not suitable for the larger subgroup size, and for larger subgroup size, in place of R we use the standard deviation chart. But it does not mean that we should not use the standard deviation method for the smaller subgroup size. We can use, but due to complexity, I have already told you that this chart technique was developed at that time when there was no computer, no calculator, no information technology, and all the calculations were done manually. So in that case the main effort was that how to simplify the calculation. how to simplify the calculation. So people normally avoid to use the standard deviation to calculate this standard deviation. So therefore, for the smaller subgroup size, in place of the S chart, we use the R chart. But for the larger subgroup size, if it is 10 or more than 10, then we should prefer the S chart in place of R chart. Now control chart for variables. What are the objectives of the control chart for variables? We can see there are following objectives. The first is to achieve the quality improvement in the product, and then to determine the process capability. Process capability means the variation of the process between the two limit. That means to find the value of 6 sigma. 6 sigma, that means plus minus 3 sigma. This will be the mean value, and this will be the plus minus 3 sigma, and this will be the plus 3 sigma. So we want to find the process capability, or you can say that process spread. Now provide the information for decision with regard to product specification, then information about the current production process, then information about the decision taken by the currently produced item. So these are the objectives which are used for the producing the control chart for variables. Now you can see that X bar R chart. How to use this X bar R chart? This is X bar R chart. X bar R chart. And in this case, I would like to discuss this X bar R chart using the numerical example, and this will be better to explain the things. Now you can see here the numerical example. Yes, this is the numerical example. Now see here. These are the different subgroups. So total subgroups are here 24. 24 subgroups are used here. So this is the number of subgroups, or you can say sample also subgroups. These are 24, but the sample size is 4. We have considered the 4 items in each subgroup. 4 items in each subgroup, so this is known as subgroup size. So there is difference between the subgroup size and the number of subgroups. So please don't get confused using these two terminology. And this is 4 here, n equal to 4, and in this presentation I have used the terminology n for the subgroup size and g for the number of subgroups. I have used this coding g for the number of subgroups and n for the subgroup size. So here n equal to 4, g equal to 24. And after placing this measurement here, we find the X bar value. X bar value means this plus this plus this plus this divided by 4. So this X bar will be equal to summation of X divided by n. Here n is the subgroup size. In one subgroup there are 4 items, and this will be here 4 items. So in this case, x1 plus x2 plus x3 plus x4 divided by 4. So in this way we can find the value of X bar for all the different subgroups. You can see here we have calculated the value of X bar. Now after calculating the value of X bar, we will have to calculate the value of R range. R means range of variation. That means what is the minimum value in these 4 value, among these 4 value, and which one is the maximum value. So in this case we can see that the minimum value is 36, and maximum value is 46. So the range of variation is 10, so this is written 10. So in the same fashion we will have to calculate the value of R for all the different subgroups, and after calculating the value of R will be equal to X maximum minus X minimum. So this is range of variation. So after calculation of this, we will find the value of X double bar. X double bar shows the average of the entire size. That means average of all the subgroups, not in the particular subgroup. So this is average of all the different subgroups. So we will have to calculate the summation of X bar. And this shows the summation of X bar, total summation of this column and this column, X bar column. So this is the summation of X bar. After finding the summation of X bar, we will have to also find the summation of R. So this is a summation of R, and we can see that what is summation of X bar. This is the formula used for the x double bar, that is summation of x bar divided by g. So this is summation of x bar, which is calculated here 990, and total number of subgroups 24. So this is the value of x double bar. Now this x double bar shows the average of the entire subgroups, not for the particular subgroups. Now this R bar shows the range of the entire subgroups, not for the particular subgroups. So this is summation of range divided by the number of subgroups, not subgroup size. So this is 24 and this is 211. This is summation of the range for the all the subgroups. So this is value 8.79. This is value of R bar. Now we have already calculated the value of x double bar and R bar. Now there is requirement to calculate the UCL and LCL. UCL is equal to x double bar plus minus 3 sigma x bar. Now you can see that to calculate the sigma value for all the x bar, and this is very difficult. Therefore to simplify this, we use the ready-made type of the formula, and this is known as x double bar plus A2 R bar. Now value of A2 depends on the value of n. Here n is the sample size. The value of sigma x bar depends on the value of n. Therefore, the in calculation of the sigma x bar, the constant term is calculated, and which is indicated in terms of A2, and the value of A2 depends on the value of n. Here n is equal to 4, so we can take this value A2 from this table, and this table is already provided in any book of the SQC. So we can see here, this is the table provided here. So in this case you can see that this value of n is shown here. This value of n is shown here, and different type of the constant A2, A3, C4, and then B3, B4, B6, B5, small d2, 1 by small d2, d3, capital D1, capital D2, capital D3, capital D4. So these are the constant, and the value of these constant varies with n. N means the subgroup size. So before taking this value, we have to consider that what is the value of the subgroup size in our question, and accordingly we should take the value. Now in the formulation of the problem, also we have to focus on the nomenclature. That means if I write the small d2 means a small d2, don't write capital D2. The value of capital D2 will be different from the small d2. Similarly, if we write a small c4, that means a small c4, don't write the capital C4. So here we will have to focus here. Then now we can use the statistical type of the concept here. Suppose this is the normal distribution and this is the mean value. This is x double bar. Then the conformance zone will be this side and this side up to 3 sigma, and here this is also 3 sigma, 3 sigma x bar, 3 sigma x bar. So this is the conformance zone. If the product lies outside this zone, this means out of control. This is out of control. Similarly, this side, this is out of control. Now all the products should lie in this conformance zone, and this is known as under control. That means if we follow this concept, that means plus minus 3 sigma concept, then what is the area of this? This area is 99.73%. Under this 3 sigma, plus minus 3 sigma, this area is 99.373%. That means there is a chance that the product will be out of control, 0.27%. And if you produce 1 million product, then this will be 2700, that means 2700 defective products. That means if you follow the concept of plus minus 3 sigma, then there may be probability that we can produce 2700 products out of 1 million products as a defective products. This is the reason that nowadays we are following the 6 sigma concept. Under the 6 sigma concept, the number of defective per million items, that means part per million items, is only 3.4. 3.4, and under this Six Sigma we have to do the precision type of the manufacturing. We have to improve the technology and entire system, and we have to use the improved quality concept. Then we can follow this Six Sigma and we can achieve the Six Sigma level of the quality. That means 3.4 part per million defective. That means this is more or less zero defective. But if you follow the plus minus 3 sigma concept, which we are discussing right now, then in that situation the number of defective will be 2700 part per million. So now I am discussing that how to use this UCL. So this will be UCL here, this will be UCL, and this will be LCL, lower control limit. So in this case, if you plot this diagram, then this will be LCL, this will be X double bar minus A2 R bar. R bar is already calculated and X double bar is already calculated, and the value of A2 can be taken from the table which I have just shown, this table for n equal to 4, because in this case the sample size is 4. So now you can see that this value is taken from this table for n equal to 4, and this is 0.729. This is value of A2, 0.729. This is value of the R bar. This is value of the X double bar, which is calculated already. Then you can see that this is the upper control limit, 47.65. This is the lower control limit. So here this is the lower control limit, this is LCL, and this is UCL, upper control limit, and this is the X bar value, X double bar value. This is also known as center line. Now you can see that how many products are out of how many subgroups are out of control. Now we place the X bar of the different subgroups in this chart. If this is X bar chart, then we have to plot all the mean value of different subgroups here. So from subgroup 1 to subgroup 24 here. So we can see that this subgroup, this subgroup, this subgroup, and this subgroup, this lies outside this upper control limit, and this is outside the lower control limit. So these four data are out of control. So if these four data are out of control, then once it is required to revise the control chart, then again and again revision is not required. The first time you will have to revise this control chart, and this will be final. And then how to do the revision we will discuss later. At first we must discuss about the R chart, because this is X bar R chart. R chart is also necessary here. So how to draw the R chart? Now you can see that for R chart, this is very similar to X bar chart, but here for R chart, this is the different formula. This is UCL for the R, and we can calculate using capital D4 R bar. Here capital D4 is the constant term, and this is again depends on the sigma of this R bar, and this sigma is calculated corresponding to the n value. So here corresponding to n equal to 4, we will have to find the value of D4 and D3, D4 and D3. And this is the upper control limit, and LCL for the R chart, this will be capital D3, D3 and R bar. So in this case you can see this is the upper control limit and this is the lower control limit. Upper control limit is this, lower control limit is 0 here. So there is only one subgroup is out of control in the R chart. So what should we do for plotting finding the revised control limits and revised center line? For revised control limits and revised center line, please remember this: we have to see that how many subgroups are out of control in X chart, X bar chart, out of control in X bar R chart. Then you will have to see how many subgroups are out of control in the R chart, in the R chart. So we have to discard this value, discard this value to find the X bar new, that means X double bar new. And again you will have to discard this subgroup in calculation of the new value of R0, new value of R0. No, don't discard these subgroups in R chart, and don't discard this subgroup in X bar chart. So we should discard only those subgroups in X bar chart which is out of control in only X bar chart, not in the R chart. There is no meaning of consideration of that subgroup in R chart. Similarly, if you want to find the new value of R bar, then again we should consider that subgroups which is out of control in the R chart. Then this must be discarded in R chart only. So you can see here there are four subgroups which is out of control in the X bar chart. So this is discarded. Now the remaining subgroups are only 20 out of 24. So this is G minus GD. G minus GD means discarded subgroup is deducted from the total number of subgroups. So this is 24 minus 4. We have discarded 4 subgroups, and the value of X bar of these subgroups are discarded from this total value. So this is the new value of X double bar. This is new value of X double bar, and this is new value of, similarly in the case of the R bar new, you can see that only one data or only one subgroup is out of control. Therefore here this will be 23 and 1 is discarded, and the new value of R bar 0 is 7.86. Now considering these two value, we will have to find the upper control limit for X bar chart new and lower control limit for X bar chart new. And in this case the constant will be different. Please remember this. In the trial case we have used the value of A2 and R bar, but here in place of R bar we will use the concept of sigma 0, and this sigma 0 will be equal to R bar new, this one R bar new divided by D2, and this value of D2 is taken from the table for corresponding value of n. If n equal to 4, then we will have to take the value of D2, as I have shown that chart also. So from that chart we can calculate this value of sigma 0. Then here we can write that X double bar new, which is calculated after revision, plus plus sigma 3 sorry, a sigma 0, not A2. Here we should use A. In place of A2 we use A, and in place of R bar we use the sigma 0. Now similarly for LCL we can use this minus A sigma 0, and for the UCL for R bar R new, this will be equal to D2. In place of D4 we use D2 sigma 0. Sigma 0 is already calculated as I discussed here. Then LCL R new, this will be D1 sigma 0, and in this way this will be the final value. That is, this is upper control limit for X bar chart, this is the lower control limit for X bar chart, this is upper control limit for R chart, this is lower control limit for R chart. So this is the revised value. Now you can see this in this problem, this is the revised value, and this value of A is taken here 1.5. Initially it was 0.7 something, because this was A2 not A. Here this is A, and here this is the D2, and this is D1, and this value is the revised R bar, and this is value of a small d2, which is taken from table for n equal to 4. So this is a d2, small d2. So in this way we can find the upper control limit, lower control limit for X bar chart, and this is upper control limit and lower control limit for R chart. This is the revised. Okay. So in this way we can use the X bar R chart. Similarly, if the subgroup size is large, then we can use the X bar S chart. S is the standard deviation, and we can use any formula to find the standard deviation for each subgroup. So for each subgroup we can find this for calculation xi minus x bar square, this is summation divided by n minus 1. So we can use this formula to calculate the value of the standard deviation. And now see here, there is only difference in the value of the constant, and rest process is same. Here in place of A2 we use A3 for the trial upper control and trial lower control. This is A3, but initially it was used A2 in the case of X bar R chart. Here in place of the D4 D3 we use B4 B3, capital B4 capital B3, and this these four value also can be taken from the table using the n equal to 4. because here n equal to 4, subgroup size is 4. And if there is any data out of control, then again we find the new value of x double bar and new value of x bar, s bar. And here we can calculate the value of s for all the different subgroups, and we can find the value of s bar, that is summation of s divided by g. Similarly, this x double bar, as usual, summation of x bar divided by g. And after that, if we see that some subgroups are out of control, then we can produce the revised value, and this sigma 0 will be now s bar nu by c4. But in the previous case, we were using r bar nu divided by d2, small d2. But please remember, here in the case of standard deviation, we use c4 in place of d2. And in the revised case, we will use the same constant, that is a, for the x bar chart, x bar nu chart, and sigma 0 will be s bar nu divided by c4 in place of r bar nu divided by d2. But here in place of d1 d2, we use b6 b5 in the revised control chart for the s chart. This is for the s chart. So this is for the revision. Now you can see here we have calculated the value of x bar here for all the different subgroups, and this is the standard deviation. And now using this standard deviation, we can find the value of summation of s and summation of x bar, and then we can divide this value. This will be x double bar, and if we divide this value, this will be s bar. So this x double bar s bar can be used here in this formula. And using a3 here, a3 value is 1.6284 n equal to 4. If we consider n equal to 4, this can be taken from the table, and this value is calculated as the s bar nu. This is the x double bar. So in this way, we can find the value of UCL LCL for x bar chart, and this is for the s chart. Now we can see that how many components are, how many subgroups are out of control. The x bar chart is very similar to that chart, so there is no difference here because n equal to 4. And if the subgroup size is small, then the result will be very similar to the s chart as comparison to the x bar r chart. So here there are 4 subgroups that are out of control here, and here there is only one subgroups. Again, you can see that in the s chart there is only one subgroup which is out of control. So these 4 will be discarded to find the x bar nu, x double bar nu, and this will be discarded to calculate the value of x bar nu. Only one will be discarded here, and 4 will be discarded here. So how to find this revised? You can see that these 4 are discarded, and the subgroup size is 20, and this is the revised x double bar nu, and this is the revised s bar nu, and this is the sigma 0 s bar nu, this divided by c4. This value of c4 is corresponding to n equal to 4, and this is taken from the table which I have already shown. Now in this way, we can use x double bar nu plus a into sigma 0, here minus sigma 0, and b5 b6, and this is the revised control chart for x bar, and this is revised control chart for s. So in this way we can produce the control chart for variables. Now see process under control, how to decide that process under control. About 2/3 data, that is 67% of the data, should be very close to the center line. That means this should be very close to the center line, this center line, and a few points, that means 5%, lie closer to the center line, the control limits. That means here close to the control limits, it should not be more than 5% of the data. The points are located back and forth across the center line. There should be balanced type of the data, back and forth both sides, not only one side. If there is only one side, then we can say that there is something wrong and we should check the process. However, this subgroup is not out of control in terms of the utility, but the process may go out of control, so we should check the process. Now, no points lie beyond the control limit. No points should lie beyond the control limit. If any points are beyond the control limit, that means this is out of control, and we should check the process. Now, this is the pattern of process out of control. So, out of control means what are the different patterns? That means we can say that process is out of control. Mathematically, this pattern cannot be followed, but if we observe the particular distribution on the control chart, then we can observe that there is something wrong in the process, and we should check the process. And process is out of control. Subgroup is not out of control, but process is out of control. So how to decide that process is out of control? That one or more points outside the control limit. This is the very basic generally which is we have discussed. Now, 7 or more consecutive points on one side of the center line. There should not be consecutive 6 or 7 or more points only one side of the control limit center line. If this type of pattern exists, that means there is something wrong, and the process is out of control. Similarly, 6 points in a row steadily increasing or decreasing. That means continuously 6 point cannot be increased or cannot be decreased continuously. If this type of pattern exists, then again the process will be out of control. 14 points alternating up and down, continuously alternating up to 14 points. That means there is something wrong. Why continuously this is doing this type of the pattern? And again we should check the process may be out of control. Now, 2 out of the 3 consecutive points in the outer third of the control region. That means if this is central line and this is upper control limit and this is lower control limit, then each control limits can be divided into the 3 subzone. This one, 3 part, this 3 part. That means 2 out of 3 consecutive points, 2 out of 3 consecutive points should not be in the outer third. This is outer third, this is the outer third. Should not be sorry, this is outer third, so should not be in the outer third. If this type of pattern exists, again then process will be out of control. Now, 15 points in a row within the center third of the central region, 15 point in a row continuously, so in the center third, so again this will be out of control. So that should be the natural type of the pattern, not the specific type of the pattern or customized type of the pattern. If any such type of the pattern exists, that means the process is out of control and we should check the process. Then the 8 points on both sides of the center third of the centroid. So continuously 8 point in the center third on one side or the other side, this will be considered as out of control. So if this type of the data pattern exists, then that means the process is out of control and we should check the process. Now, region for process out of control. What are the different regions? This may be the change or jump in level. That means this is maybe the chance cause. Then trend or the steady change in level. Then recurring cycle. After certain cycle, again it recurs due to heating of the engine or anything. That may be the region. Then two population on the same machine. If two workers working, then there may be the variation in the quality and there may be the process out of control. Then mistakes may be the region for the process out of control. Now see this process capability concept. Now we are discussing about the central limit theorem, and central limit theorem, that means if we take the sample from the non-normally distributed population, that means if the population is not normally distributed and we take the sample, then if the sample size is 4 or more than 4, then the sample average will tend towards the normal distribution. This is a central limit theorem. So in the population from which the samples are taken not normal, the distribution of the sample average will tend towards normality, provided that the sample size n is at least 4. This tendency increases as sample size increases. So here Z is to be calculated using this is the standard value of X we use in the standard normal distribution table. You can see that this is the standard normal distribution. Then if we show the X value on the x-axis and this is the PDF probability density function on the y-axis, then this value, mean values, is shown here, and this will be the x value. Then to convert these value into the standard form, this Z is used. So this is known as standard value. This Z will be equal to x bar minus mu by sigma x bar. Sigma by x bar. Here x bar is this value is x bar. So mu is here x double bar. double bar. So in this case we can use this value. Now the process capability index, how to find the process capability index? So we can see here that process capability index is shown in terms of CP. This is known as the capability index, and this is shown as U minus L by 6 sigma 0, 6 sigma 0. So sigma 0 is the process spread. So this is difference between the upper control limit and lower control limit. This is 3 sigma 0. This is 3 sigma 0 this side, and 3 sigma 0 this side. So total this will be 6 sigma 0, and this is the x double bar value, and this is the UCL, and this is LCL. Now if this type of pattern exists, that means UCL and LCL, upper control limit and lower control limit, lies inside the specification limit. There is difference between the specification limit and the control limit. Control limits are calculated based on the production, after production, but the upper control limit, upper deviation limit, that is the specification limit, and lower specification limit is determined by the design engineers or manufacturers before the manufacturing of the product. So the control limits must be inside this upper specification limit, or the lower specification limit. So this is U minus L divided by 6 sigma. This difference between the upper specification and lower specification limit, this is known as U minus L. U minus L, but difference between the upper control limit and lower control limit, this is UCL minus LCL. This will be the 6 sigma, total 6 sigma. So this should be greater than 1. This should be greater than 1. If this is greater than 1, that means this is desirable, and all the control limits lie inside the specification limits. If it is 1, suppose this is 1, that means U minus L equal to 6 sigma 0, then this will be equal to 1. So this is the second situation which is shown in figure B. But this is alarming situation at any time if the UCL and LCL crosses this line, because there is a coincidence between the UCL and U and LCL and L, but at any time it may go outside, this may go outside, then this will be completely out of control. So this is the alarming situation. It should not be 1. Now if it is U minus L divided by 6 sigma is less than 1, that means this is undesirable, process is out of control, since upper control limit is outside the specification limit. So the value lying here, this may be the out of control, so this is not desirable, so we must avoid this. So how to avoid this? We have to check the process, and we will have to improve the quality. Now see this process capability, how to calculate this process capability index. Now take the 20 subgroup size of 4, that means we consider the 20 subgroups. Suppose this is subgroup number, then this will be 1, 2, 3 up to 20, and the subgroup size will be of 4, like this, and find the value of X bar and find the value of S for each subgroup. After finding this, calculate the sample standard deviation. This is then calculate the average sample standard deviation. That means this is summation of S divided by G. G is here 20, and this will be S bar. Then this S bar is summation of S divided by G divided by 20. Then after finding the value of S bar, we can find the value of sigma 0. This sigma 0 will be equal to S bar divided by C4. This C4 is taken from the table for n equal to 4. So after putting this value here, and this is already calculated, we can find the value of sigma 0, and this sigma 0 can be used in the denominator 6 sigma 0, and the value of U and L, it is already given because this is the specification limits. So in this way we can find the capability index. Now this is the example which is based on the capability index. You can see that using the data provided in the example, find the process capability index. Upper and lower specification limit is given as 50 mm and the 30 mm. This is given. So this is U and L. This is already given, and rest data is taken from the example 1 which we have discussed. Here C4 is given as 0.9213 corresponding to n equal to 4. So here this is the C4 value, and we can take the value of S bar from the previous example. So this is 3.9 divided by C4. So this is value of sigma 0. Now we can put the value of 6 sigma 0 here in the denominator, and we can find the value of Cp is equal to 0.788. But Cp must be greater than 1. Must be greater than 1, but this is less than 1. This is less than 1. So this is not desirable. This is not desirable. So we should check the process to improve the system. Now limitation of control chart of variable. Control chart for variable. So it cannot be used for the attributes type of the quality characteristics. This is the one of the limitation. Second, if the product has a large number of variables, that means a large number of the quality parameters, then for each parameter we will have to plot the separate control charts, which is very difficult. So this is the another limitations. Now thank you, and in the next session we will discuss about the control chart for attributes.